Good morning, students. Welcome to the class of Introduction to Cognitive Robotics. In this lecture, we will focus on the dynamics of a single neuron itself. So far, I have given you the morphological description of a neuron, that what does a neuron consist of, and what are the different parts, and what are the different types of neuron. But now the time has come for us to focus on the neuronal dynamics, because only if we understand the neuronal dynamics, we will be able to understand how a group of neurons will work together, and then we will be able to understand that how these manifestations of networking of neuron would actually affect the cognitive aspects of, let us say, Homo sapiens or any such other living beings with group of neurons associated in relation to their brain action. So it is extremely important for us, to understand the neuronal dynamics so that we can understand finally its manifestation in terms of different cognitive aspects. It is also important for us when we will be developing a cognitive robot. In the other side, in terms of the development of the robot, we have to understand that similar to these neuronal networks, we have to develop some artificial neuronal network of kind of similar complexity. So hence it is absolutely essential for us to understand the neuronal dynamics, which is what we will be trying in today's lecture. In this lecture, I will mostly focus on Hodgkin-Huxley model, which is a classical model of a dynamic model of a neuron, and based on the 1962 Nobel Prize of Hodgkin and Huxley. So that we will focus the governing equations, the conductance versus gate relationship, the gate variables. Then we will talk a little bit about neuron as oscillator and the Winfree model. So that will be the flow of this lecture. Now, before we talk about the HH model itself, let us first see that how the action potential gets generated inside a neuron, because ultimately the dynamics of the neuron will be governed by the dynamics of the action potential, how the action potential moves with respect to different opening of the gates. That's what will be ultimately mattering. So let us look into that. If you look at the excitation at the neuronal level, and then what you would see is that, let's say there are many inputs that a neuron will be gathering from its dendrites. Now there are two types of dendrites. There are some called basal dendrite and some called apical dendrite. Basal dendrites are directly related to the soma, and apical dendrites basically come from far away and through a channel that actually comes and sends the signal to the soma. But right now, let us consider that there are n number of inputs that are coming to these dendrites into the soma, which is the cell body. So if we look at this procedure, so you have these inputs are coming from all over. Okay, so signals are connected by neurons from the dendrites. That's the first part. And then the soma, basically it will work like an integrator. So the cell body soma sums the incoming signals, both spatially as well as temporally. So let us say that if there is one signal coming from this part, another signal coming from this part, then inside the soma, this will become a, something which will be an integration of these two signals. Okay, so it will be somewhat more than what was there. Of course, the signals will be little bit of decaying as it will be coming from these sides towards this distance. Okay. However, if the two signals are actually they are at the same time, then there is a good chance that they will be integrated. These two dendrite signals, they'll be integrated here, and you will be getting, so in terms of spatial integration, like that, if there are n number of channels which are contributing, say one more channel is also giving, so you will be getting an even higher signal. Okay, so that's how the signal integrations will happen at the soma. Now, when sufficient input is received, in fact, a threshold, of course, there is nowadays people have discovered that there is not a fixed threshold, but there is a threshold band. But whenever this threshold around that region it is exceeded, then only the neuron will generate an action potential or spike. This is also called firing of the neuron. So this will happen around this area. Okay, this is where the firing of the neuron will start, and then that action potential will start to travel. So the action potential then is transmitted along the action. That's how it is going, and finally it will go to other neurons. So these axons will generate the action potential. It will come here, and then from these synaptic junctions it will go to all other neurons. So Y1, Y2s are different outputs that are going to go to different m number of neurons. And if, however, sufficient input is not received, then the inputs will quickly decay and no action potential will be generated. So the timing is very important. The more input signals will arrive together, the higher the chance that there will be a strong input which will come. And the more number of the inputs will actually be integrating, there also is a higher chance that this input is going to exceed the threshold level, and hence the action firing is going to take place. Let us look into it with respect to a practical case. So we have talked about, if you remember, the reflex action. So let us look into it in terms of the reflex action. If you remember that in case of a reflex action, the nerves are the afferent nerves were actually linked with the muscle spindle. So this is where is the muscle spindle. So whenever we were actually giving a little bit of heating, there is a stretching that is happening, and this tweaking of the muscle spindle is actually getting the triggering in terms of the neuron, and that triggering is coming through the myelinated action to the cell body, and from there further it is going to the synaptic terminals. Now if you look at it, that the initial stimulus of the signal, the duration of it is important. Okay, so if this is the initial signal, there will be a little bit of degradation of the signal, and finally that initial signal will create, if it crosses the threshold, so because this is above the threshold level, the usual resting potential is about -60 millivolt, and about -50 millivolt you will get a threshold level. So this will be around -50 or so. Okay, so this varies, but roughly it is about -50. If it is above this, then you will see that there is a spike that is forming, and as many number of times this is happening, that many number of spikes will be forming. So these spikes are formed, then the spikes are traveling, and at the output level this is actually creating the neurotransmitters. Now if the signal continues with a higher value and for a some kind of a high intensity values, then what can happen is that once again it will check that whether it is above the threshold level or not. So if it is above the threshold level, then the spike intensity may actually increase. Okay, so the frequency of the spike, not the intensity, the frequency of the spike, generally the spikes actually the amplitude will not change. Okay, you can see here also it is about 20, here also it is about 20. So this is not going to change, but between this signal and this signal, because this signal has, the input signal has a higher intensity, what you may see that it will get reflected in terms of more number of action potential spike. So there will be more spikes. There will be greater spikes in this case. Okay, so the spikes will be higher in this case, and that would mean that the neuronal firing will be actually higher in this case. Okay, so that is what we have to greater spikes. Okay, greater spikes will be there in this case. So that's what we can see. In fact, the other case, suppose if the duration is longer, in this case the duration is longer, so it is above the threshold level for a longer period of time. And in that case, what will happen is that now the number of spikes the density of the number of spikes will be something like, you know, that it will be not affected, but it will be more in terms of the duration of the spike. That total duration of the spike initially was smaller, here it will be bigger. And another thing also, you can see that as the resting potential, as the graded potential is degrading, you can see that here also the density of the spike that is actually getting lighter and lighter. And accordingly, you would see that the generation of the neurotransmission in different cases will be different. So finally, that will be the output of the system. So this is how typically a neuronal dynamics will actually happen. In this case, it is for a reflex action. Now, there is one point that we have to always keep in your mind, that in the beginning, a particular neuron will be always at its resting potential level. So it will be at its resting potential. Okay, so wherever is this resting potential, it will be at that level in the beginning. In this case, it is showing that this is the resting potential level. Usually it is up to minus 60 millivolt. So that is where it will be. So that is the resting potential. Now once the charges or the inputs are accumulating, then what you will be having is called the graded potential. So basically this happens when a lot of sodiums are actually rushing inside. So there is a movement of sodium that happens. So in this part there is a lot of sodium which will be actually sodium plus, which will be actually going inside the neuron. Okay, so basically what happens is that in a neuronal cell, the inside part of the neuronal always maintains itself with a negative potential. So as the sodium will be going inside, then you see that from the resting potential it will be actually going up. So that is what it is happening. It is going towards the positive side. Now this is something that we actually call, there is a technical term for it, it is called depolarization. Depolarization. So that's what is going to happen to the system. So as more and more sodium is going to go inside the cell, there will be more and more depolarization of the cells. Okay, so that's what is the first phase, and that's why it is crossing the threshold level and it is going to a high level. And as soon as this happens, immediately the action potential will be released. That means immediately there will be a spike that will come up. Now, once there is sufficient sodium, then these sodiums which are plus, right? So they will start to repel each other, and hence they will spread inside the system, and they will also further reduce the inflow of the sodium. So that will come down. That's why you can see that the potential is coming down. Simultaneously, there is a potassium movement that will start to happen. So this K plus is going to leave the system. This happens slowly. Okay, so this will create the hyperpolarization, and that will create actually the further negative part of the signal. So depolarization will actually inspire the action potential generation, whereas hyperpotential will actually create, negative of action potential. It will not allow the generation of action potential. We have to keep this in mind. That's why in any common signal, it will be the firing action potential will be something like a spike followed by a slow negative side until it comes back to the resting potential. So that's the very common pattern of a signal that you will find in any neuronal signal. Now, the other point we have to keep in your mind is that the more the receiving signals are, like 4 synapses, 8 synapses, 16 synapses, you are going to see that this graded potential is going to increase, and that will create finally the generation of the action potential. However, as I told you earlier also, that the magnitude of the action potential by and large remains constant. That does not change. Only if the intensity is very high, it may result on many high density action potentials. Okay, and if the intensity is low, it may result on few action potentials which are separated with respect to time in a much lighter density. Okay, so these are the common things that we have to keep in our mind. The other point is that during the hyperpolarization phase, okay, the cell generally would not, the neuronal cell generally would not initiate one more action spiking. Particularly, there is one region up to this region, okay, which is also called absolute, part of the hyperpolarization. So this is the absolute part. Okay, so it is absolute hyperpolarization. There, it will not allow any firing of the action potential at all. But it is the later part, this part, which is known as the relative part of the hyperpolarization. This is where it will allow a firing. If at all required, it will allow the action potential to fire. So these are the points we have to keep in our mind in terms of the neuron action potential. Now that you know about that how an action potential gets generated in a neuron, let us look into that how we can mathematically define this action potential generation in the system. Okay, so and to do that, we will take ourselves to the Hodgkin-Huxley theorem, which is the classical theorem of explaining this neural dynamics. Later on, we will see that this theory further gets modified. But let's start with the very popular fundamental theorem which governs this. So we will now talk about the discovery of the nerve impulse flow from a squid giant action. That was done by Hodgkin and Huxley in 1952. And as you can see that they both Hodgkin and Huxley working on a giant squid. So this become like a legendary photograph. That was the first time that the record of a typical action potential of a neuron that has been done actually. Now the reason why they had chosen the giant squid action, the action of a giant squid, is basically because this is quite thick actually. So it was easier in those days to carry out the experiments and to see the action potential. Okay. Now, so you can see here that typically how this action potential signal is. But you have to, of course, cross the threshold level in order to see this firing that is happening into the system. And you can see that there is a squid here, and you can see that the nerves which are associated, the nerves you can see here, which are associated with the giant squid giant actions they call it. Now this is used by the squids, by the by, for their escapes, for all emergency purpose. So let us look into it. Let us look into that how generally the squids actually propagate. As you can see that this is how a squid is generally propelling, and at that time it does not use much that giant action that is there for the squid. Okay, so this is how they are tracking. But you will see whenever emergency comes, how fast this squid is actually going to work. So if you continuously follow that how it's happening, and you can see that this is the squid, and suddenly you will see that this is the point where it has actually given this kind of a signal, and then it is happening at a very fast rate. Now let us look into the Hodgkin-Huxley model that has been developed based on the experiment on the giant squid action. Now, what is the nerve speed that was there in this particular case? Well, this is about 30 meters per second. So that is the kind of a nerve speed, and that means it will be about 108 kilometers per hour. So something like a very high speed car or a very high speed train that you see, that will be having this kind of a nerve speed. Now, for your information, for human, muscle fiber control speed is something like 425 kilometers per hour, almost like the aircraft's taking off speed. And the touch is about 274 kilometers per hour, almost like a bullet train speed. However, the pain signal that goes at a very slow speed, something like 2.2 kilometers per hour. So this is just a reference that where we are in terms of the giant squid speed, which is not very high, not very slow. Now by fixing electrodes into the nerve cells, they call it voltage clamp, then they have actually, they have been able to excite, and they can see this spike which occurs generally in the millisecond level, thousandths of a second. In the millisecond level, this reaction happens. It is correspond to 30 meters per second. So the cell membranes are electrically polarized, and a difference of electric potential exists, as I told you, in general, that is in the negative side, and that happens, and this change also. So this all happens because of the presence of the ion channels. Okay, so there are three different types of ion channels: the sodium ion channel, potassium ion channel, and leakage channel, and also there is a calcium channel. So in all about four, but in our model we'll consider three: sodium, potassium, and leakage channel. The calcium we would not consider in our model. Now, so what happens, as I told you, that there is these sodiums which will be rushing inside, okay, and then it will be followed by the potassium which will going out of the nerve cell. So that would create basically this kind of a positive and then followed by a negative signal. Okay, so there will be a part A, which is the rise of the potassium conductance. It should be actually not potassium, sorry, it should be sodium conductance. So that is one part, and followed by B, in which there will be the potassium conductance part of it. Okay, so let us look into the Hodgkin-Huxley model now. So as we will be actually applying the capacitive current IC, which is defined by the rate of change of charge Q at the membrane surface. So IC is the rate of change, that is dQ dt. Now the charge Qt is related to the instantaneous membrane voltage VMT and membrane capacitance Cm. So you know that there is this relationship that exists, which is Q equals to Cm Vm. Now the ionic current ion, if I try to actually represent what is happening inside an action potential in terms of a simple electrical circuit, then you can consider it to be something which is a combination of, you can say, resistors of variable resistance. So these are the resistors, and that is basically shown in terms of conductance, and also these are the capacitors. So a combination of them, and as you can see that there are actually three of them that is used in this model, that is the sodium, the potassium, and the leakage. Generally these three, okay, that is used for this case. Now the ionic current I ion is subdivided into three distinct components. That is the sodium current part corresponding to the sodium part of it, and then a potassium current part IK, and a small leakage current IL, and which is primarily carried by the chloride ions. So these are the three currents that are actually streaming into the system. So and that's the full system along with the capacitance corresponding to each one of them. So you can write a mathematical equation, and which is like the Cm is the membrane capacitance. So Cm is the membrane capacitance, okay, and Vm is the voltage that you are actually, either you are applying the voltage or you are measuring the voltage, membrane voltage, and I ion, okay, that's the current that is actually passing through the ion circuit. So that's the I ion part of it, and then I external, that's the externally applied current. So in this model we are applying the current from outside. As a result of it, this will actually generate I ion, and also it will generate these dVm dt, and that is related to the capacitance. Okay, so these are the two things that this I external is going to develop. Now I ion itself are actually can consist of 3 or 4 parts of it. So it depends on the conductance of each one, as I told you, sodium, potassium, leakage, like that, and then the difference, so that conductance times the difference between the voltage Vm of the membrane potential minus the equilibrium potential Ek, so that will give us the ionic current, each ionic current. So that's what will be actually, this equation will tell us. Now, in the macroscopic conductance of the HH model, this will be actually a combined effect of many microscopic ion channels. Okay, so it is not just one single ion channel. There are many ion channels which are coming into it. Each individual ion channel can be thought of as containing one or more physical gates that regulate the flow of ions through the channel. An individual gate can be in one of the two states, that is permissive or non-permissive. So this is either it will allow the ion to move inside the neuron, or it will not allow. So at some point in time, let's say PIT is the fraction of gates that are in the permissive state. That means it will allow the, let's say, the sodium to come inside. Then 1 minus PIT must be in the non-permissive state. So the probabilistic variation in terms of rate constant, let us say alpha IV is fraction which will go from non-permissive to permissive state, and beta IV is corresponding to that which will take it from permissive to non-permissive state. So this is the dynamics that will continuously happen. So at any point of time, that means the fraction of gates that are actually in the permissive state, dPi dt, it will depend on two things. One is that this weightage of alpha, how many are actually contributing to it, and in a 1 minus pi stage, okay, so alpha times 1 minus pi, and then how many are in the other way transmission, permissive to non-permissive, so that is beta times pi. So this ratio of alpha and beta is going to actually give me the dPi dt, which is going to tell me that what is the fraction of gates that are in the permissive state. So a steady state value of this equation will be something like PIT tends to infinity, and that will be coming up if I actually put this as 0. You would see that it will be alpha over alpha plus beta. So if you solve this, you will see that Pi would become alpha over alpha plus beta, and the corresponding time constant is 1 over alpha plus beta. Now let us say the conductance of the gates, let us call each one of the conductance of the gates in terms of Gk. So the conductance of the gates as Gk, so it will be each individual conductance and that product of this probability of the opening of the gates. So it is GK times product of the PIs. Okay. So let's say we are talking about the sodium channel, then there is a gain there, GNA times PM cube times pH. Okay, we will call it as M cube H. Okay, and similarly for the potassium channel, this is GK Pn to the power 4. We'll call it potassium GK. This should be GK N to the power 4. And these are different types. So now by putting these conductance into the ionic equation, I can write that the sodium part is GNA M cube H. Okay, so GNA M cube H times Vm minus ENA. Then I can write the potassium part as GK N to the power 4 Vm minus EK, and then the leakage part, that is GL times Vm minus EN. So that is how the conductance are related to the gate relations. Now this M, N, H, these are all gating variables. Let us look into it, how these gating variables itself changes, because they are the things that actually control the ionic current flow in the neuron. If you look into the gating variables, you would see that there are three gating variables that we have considered in this model, M, H and N, and their values will be always between 0 and 1. So if MQH is equal to 1, then the sodium channel is open and that conducts with the characteristic conductance GNA. And if N to the power 4 equals to 1, then the potassium channel is open and that conducts with the characteristic conductance of GK. So each one of them, this will happen only when MQH is 1, then the sodium channel will be opening, or N to the power 4 is 1, then the potassium channel is going to open. And as you can see, with respect to time, you can see that for each of the cases, like this is the N to the power 4, and you can see that how this N to the power 4 with respect to time, how this will be changing and how this GK will be changing. So you can in fact draw a best fit curve for each one of these conductance versus the time data, so that you would know how with respect to time the conductance will be changing or the gate variables will be changing. This you can do for all the gate variables. Now based on all these things together, you can actually write the final governing equation which is corresponding to the HH model. So the core of it is this first order differential equation, okay, that is the capacitance times the dVm dt plus I ion equals to the external current that is actually used for excitation of the neuron. Now the I ion itself, as I told you, will be having three parts in it. One part, that the sodium part, which is governed by the MQH, which if it is equals to 1, there is a current, the sodium current, then there is a potassium current which is governed by N to the power 4, and then there is a leakage current, GL. And each one of these, how many part of fraction of actually the sodium gates will be participating, that is governed by this simple first order relationship, that dm dt is alpha times 1 minus m minus beta times m. Similarly, dh dt alpha times 1 minus h minus beta times h, and dn dt as alpha times 1 minus n minus beta times n. So a series of first order equations are to be solved along with the ionic current equation, which is a nonlinear equation, in order to obtain that what will be, let's say, the voltage of the membrane, how that will be changing with respect to time. So far, I have talked of neuron as a dynamic model and how the voltage spike, the origin of the voltage spike, how the voltage will be changing with respect to time as you are applying an excitation current into the system, and how you can explain it in terms of different gating variables. Now we will see that instead of a time domain representation of a single firing, if a neuron starts to fire continuously, can I model that in terms of what you call an oscillator? Now it is known from the nonlinear dynamics representation of a system that whenever a system actually starts from a quiescent level, it is completely placid, the neuron, before the firing of the action potential, to kind of a oscillator level where the signals are oscillating. So initially it is under a quiescent state, then it starts to oscillate. This kind of a behavior is called a bifurcation behavior. And there are different bifurcations model that can actually explain it. So let us look into the neuron as it fires action potentials with respect to time, how we can model the neuron as an oscillator. Let's look into that. Then we will see how we can feed different bifurcation models into it. Now here we are talking about a neuron as an oscillator. And as you can see here, that this particular signal, this is actually the action potential, the firing of the action or the action spikes that is happening. So that's the action potential with respect to time. And you can clearly see that's the depolarization phase, you can see, and how the sodium currents actually come down. So you can write it as the depolarization phase. Okay, so write it as depolarization, slightly far apart. This is the depolarization, and then you can see that this is what is the hyperpolarization phase, this part below the threshold. So that is what is the hyperpolarization, and you can see how this spiking is happening. Now let us say that I would not look into it in terms of, this is of course with respect to time, I would not look into it with respect to time, but I would look into it in terms of this MH or N, which actually represents the different ionic currents. Okay, so if you look at it, that for example, how the ionic currents are varying as the spiking is happening. So let's look into it from this point of view, that here we have three axes. We have H, N, and we have the voltage. So this is the voltage axis in it. Okay, so to begin with, let us say that we have a low voltage, and then suddenly the voltage is increasing once this threshold is crossing. And as the threshold is crossing, and then we will see that there is, initially there is a value of H that we are having, okay, and as the threshold has crossed, then we can see that the value of H is actually decreasing, and it has decreased to a low level, and you can see that the N has started to increase. Now if you remember, it is the N which is related to the potassium part of it, right? So that is, once again increasing. So this is what it is continuously happening in the system, that H decreasing, N increasing, further H changing. So that is what continuously happens. And this actually can be modeled in terms of an oscillator, that the states, if I consider the H and N to be two states, then the states themselves are actually forming a circle in a phase diagram, which can be depicted in terms of an oscillator. That's the basis of a neuronal oscillator model, just for two activation states H and N. Now if you consider M, H and N, then it will become a three-dimensional space. So as I told you that these oscillators, this type of oscillators can be actually modeled mathematically in terms of three different types of bifurcations: a saddle node, Hopf bifurcation, and homoclinic bifurcation. But out of them, mostly our discussions will be for the first two cases, that is the saddle node and the Hopf bifurcation case. Now these bifurcations, how do they look like? The bifurcation diagram, if you look at it, then you would be able to see that for the saddle node there is one node which is stable and one which is unstable. So corresponding to the stable node, so whenever there is a this kind of the quiescent mode is actually getting countered by the generation of the action potential, then suddenly this frequency will start, and in the stable node this will create a spiking of the actional signals. Okay. Now there is also a possibility of two neurons joining together. In such cases, what can happen is that the signal of one affecting the other may actually create a kind of a bifurcation in which you can see that it is initially at a stage and then it actually goes out and create a new limit cycle. So it's a much bigger limit cycle. So this is where the oscillation will start. So this is a smaller limit cycle. It's a small kind of oscillation. This is the bigger one as the neurons are actually getting synchronized. So that is the Hop bifurcation case. So these are the two, the saddle node and the Hop bifurcation, which we will mostly see for the neurons as an oscillator. The third one, which is a homoclinic bifurcation, as you can see the bifurcation diagram here, that is something that is not very natural for the neuronal oscillation system. Let us now look into a very simple model of two neurons joining their hands and how a neuronal oscillation pattern can form out of it. Let us look into the network of the oscillators. Now, to understand that, you have to consider two neurons, like the two neurons here. They can take inputs from the apical dendrites, as I told you, that is far away from the soma, or they can also take input directly from the dendrites which are directly on the soma. These are called basal dendrites. And based on the integrations, let's say the action will be fired, and then you will be getting a spike like this. Now there is a synaptic junction here where the spike is coming and the neurotransmitters are getting released, and that, let's say, it is taken by the basal dendrites of the second neuron, and also some other signals are coming from the apical dendrites. Based on that, the firing happens. So then the two neurons are actually, these are the two pyramidal neurons actually found in brain. So they start to correlate with each other. That means as one is firing, the other also starts to fire. Now, what happened is that initially these different neurons can have different frequencies. But Norbert Wiener actually hypothesized that even if initially there are different neurons which are in a cluster and that are operating at different frequency levels, but with respect to time, you will see that there is a pulling effect that is happening. You can see that, say, two neurons here, one is at a higher, one is at a lower level, and one neuron which is around this level. And you can see that these two are also pulled together, and somewhere close to train Hodge, they are going to merge together. Now, whenever this en masse is happening, that means these oscillators are pulled together to come into a single frequency. This is what we will say that the neurons are getting synchronized, fully synchronized. Now, if a neuron is actually having a frequency of firing too slow, it will try to speed it up, or if it is too fast, it will try to slow it down, such that it will finally hit into a common platform of a particular frequency. In this case, Wiener has shown this with respect to the human alpha waves, which is of this kind of a low order between 8 to 10 Hz. Now, Winfree had proposed a probabilistic model based on this, and he said that this is not only for the neurons, but also it is similar phenomena is found for lots of things like chorusing crickets, flashing of fireflies, and of course the circadian pacemaker cells. So these similar events happen. And to explain these, one can actually do it with respect to the phases of each one of the individual oscillator. So the first order relationship of the phase, the rate of change of phase will depend on one frequency, which is the kind of the frequency of that system, along with, you can see that there are some constants, the influence functions, for example P, and the total number of oscillators, the coupling strength between the two of these neurons, and also the sensitivity function. So using all these things, there is a coupling part that is going to dominate. Okay, so and these two things, omega I and this part together, they are going to define the rate of change of phase in a system. So that is the Winfree's mean field model. Now Kuramoto, the famous scientist from Kyoto University of Japan, has actually expanded this. So Kuramoto put this Winfree's intuition about phase models on a much firmer foundation, and he used the perturbative method of averaging to show that for any system of weakly coupled nearly identical limit cycle oscillators, there is a long-term dynamics which can be given by the phase equation itself. And that is something along with the chimera state, which actually make this pretty famous discovery. We will study this in the next lecture. So in the next lecture, we'll talk about synchronization, classical Kuramoto model, the mean field approximation, stationary synchronizations, etc. So this is what we'll do in the next lecture. Thank you.